the generalized chart for change on enthalpy at constant temperature. In section 44, equation H2 minus H1 at constant temperature was expressed as this relation. GPT. This equation is appropriately used when a volume explicit equation of a state is known and a volume explicit equation otherwise, it is more convenient to calculate isotherm change in the internal energy also for this with this relation. Round P on round T at V constant pressure, and then calculate the change in enthalpy from this definition. I can also calculate the change of enthalpy H2 minus H1 U second Z2 minus Z1 to determine the change in enthalpy behavior consistent with the generalized chart figure D1. We follow the second of these approaches since the Lee-Kessler generalized equation of a state is a pressure explicit form in terms of a specific volume and the temperature. The Lee-Kessler generalized equation is expressed in terms of compressibility factors, so we can write Z multiplied to the RT on V equals to P, where therefore, substituting in equation 31, the equations for du RT2 on V rho Z on 1T V dV. These equations comes from the 31 equation in this chapter, which is expressed as this relation dut T multiply around T V minus P the Vt. And now with this equation we can simplify this equation with this relation for any two variable, for any two for volume and temperature in this. So that in terms of reduced variables, du Tr and Vr dV prime R. This expression is now integrated at a constant temperature from any given states P, R and Vr prime. Let me write the equation in the next page. PR and V prime R integration for any given state. PR and V prime R to the ideal gas limit when P star R and V prime star R. The subscript star will always denote an ideal gas state or property, causing an internal energy change or departure from the ideal gas value at the given state. We can write this relation. RTC V prime R on Z on TR V prime R dV prime. The integral on the right hand side of this equation can be evaluated from the Lee-Kessler equations. The corresponding enthalpy departure at the given state is then found from integration of this equation. Enthalpy departure H star minus H RTC U star minus U on R TC plus TR Following the same procedure as for the compressible factor, we can evaluate this equation with a set of Lee-Kessler simple fluid constants to give a simple fluid enthalpy departure. The value for the enthalpy departure are shown graphically in figure P2. Use the enthalpy departure function is illustrated in examples available in the chapter. Note that when use computer software for determining enthalpy departure at a given reduced temperature and reduced pressure, accuracy can be improved by using the eccentric factor in the same manner as well as done for compressibility factor in equation 58. The next section is the engineering chart for change of entropy at constant temperatures.